Our project investigates the development of an advanced plagiarism detection system with the help of latent semantic analysis. Plagiarism detection has become increasingly critical in academic, publishing, and educational contexts as digital content proliferates, making unauthorized text reuse much more prevalent. A 2019 study of university students in Australia found that 64% had engaged in some form of plagiarism at least once. Our system aims to preserve intellectual property rights, uphold academic integrity, and ensure proper attribution by identifying semantic similarities between documents. Traditional string-based or syntax-based approaches often fail when text is paraphrased or synonymy is employed. By contrast, LSA leverages linear algebraic techniques to uncover latent conceptual relationships, which means that we are searching for what the word stands for, not just the textual structure.
The first important part of our project is pre-processing. It turns a sentence into a form that is easier for a computer to handle. It also follows 5 main steps that you can see at the bottom of the screen. I'm going to use this sentence that you see to show you how the pre-processing is done. So first we need to put each word in our sentence into lowercase. Then we need to get rid of all of the punctuation marks and the stop words, which are essentially just linking words that do not give us any new information. Then we tokenize our sentence. Usually the tokens are the words themselves, as it is in this case. And then we apply lemmaization, which is essentially turning every token into its base form. So after pre-processing, our sentence, "Our project is the best," turned into a set of tokens, "We project be good."
To construct the semantic representation of our corpus, we first generate a 10-document matrix A of size n over d. N is the vocabulary size, so the amount of words, unique words we have, and D is the number of documents in our corpus, the total amount. Each entry in A is computed using temp frequency inverse document frequency, a weight. It's defined as TF multiplied by IDF. The TF component is the count of word I in document J divided by the total amount of words in document J. IDF is the logarithm of D, the amount of documents in our corpus, divided by the amount of documents containing the term I plus 1 for cases when the logarithm returns 0 to balance the weights. Applying TF-IDF emphasizes distinctive terms while downplaying those that appear multiple times.
So after TF-IDF, we have this big matrix containing the information about every word document pair there is, and we want to make it smaller, for which we use singular value decomposition algorithm. We can change this original matrix into 3 matrices U, sigma, and V transposed, whose sizes you can see on the screen. Matrices U and V transposed are orthogonal and contain right and left singular vectors of our original matrix respectively. And the main diagonal of the matrix sigma contains the singular values of the said original matrix. Now that we have this decomposition, we can use its truncated form, which is choosing k singular values that are most important and transforming U and V transposed accordingly. The way we choose k is that we looked for the number of singular values that still hold 90% of the impact. From this, we can choose any combination of 2 matrices and create a new smaller matrix that we're going to use later.
Once the truncated SVD with k top singular values and the respective singular vectors is computed, we project our reference documents, so the corpus from the beginning, into this k-dimensional semantic space using D. Here, sigma k contains the top k singular values, and vk transpose is the truncated right singular matrix. In this reduced space, each document is represented by a k-dimensional vector which captures its latent semantic characteristics, so the meaning of the word itself. We then compute pairwise cosine similarities between all of the documents and analyze corpus-wide relationships. Also, if a query is given from user, an individual document, we compute individual cosine similarity between this query vector and each reference vector from our corpus to detect potential plagiarism or semantic similarity. The values obtained are then compared to a threshold. We obtained it via test matrix. If this threshold is exceeded, we can make a statement on this document being suspicious for plagiarism of one of our corpus documents. We implemented the beginning of our algorithm with the aid of NLTK, a natural language processing library. It helped with text preprocessing and the TF-IDF weights computation. Then we used a manual implementation of SVD at the core. The code provides a visual representation of k, which captures the chosen amount of variance, and then at the very end, it shows the cosine similarities, either between the corpus itself or between the corpus and the chosen query from user. While implementing, three various corpuses were used. One of them, initial, are a small and customly created corpus which contained about 8 originals and 8 plagiarisms of various degree. Then a benchmark dataset, then plagiarism corpus 2011 with a similar structure, but a much larger size, to see if larger amounts of unique words and sentences would really help with synonym detection. Finally, for the test metrics, a dataset created by Claw and Stevenson was used. The suspicious documents there mimic student answers with various types of plagiarism to a select amount of original tasks. This dataset has labels for various types of plagiarism, so hard, light, and cut, then none, so no plagiarism, and that allowed us to use it for algorithm evaluation.
Show you a way to check whether our algorithm was successful. We decided against using accuracy itself as a metric because it does not cover all of the edge cases, but we opted for using the combination of precision and recall. And both of the formulas you can see on the screen, and the first one shows us how many of the predicted positives are actually positive, and recall shows us how many of the actual positives were predicted correctly. The combination of them, specifically the harmonic mean, creates a F1 metric. However, we have more than 2 classes, so what we use is called macro F1 score, which is essentially calculating F1 score for each class individually and then getting an average of them. Here is one example of our results, which can be interesting because it is quite low. It is not an expected 90+%, it's only 45.5%, which is still sufficient for our case because, as I mentioned, we have not just not plagiarized at plagiarized states, but we also have low and high plagiarism. So thanks to that, we can see that the F1 score of 45% is actually representing a successful algorithm and says that our predictions are true most of the time. In conclusion, yes, our algorithm is not perfect. It can be slow if you put a lot of data into it, and it is not perfectly precise because of the truncation of SVD. However, it is incredibly easy to implement, and it does not need much data or computational power, as for example a large language model would have. It also really quickly reaches the threshold of being effective, so even when you have small amount of data, and this algorithm would still efficiently help you to identify plagiarism, so it can be used as a much less demanding but still almost as efficient replacement for LLM.